Welcome to today's class on electricity, class 10, chapter number 12. You know that electricity has an important place in our today's modern society. It is a controllable and one of the most convenient form of energy for a variety of uses in homes, schools and hospitals, industries and so on. In this lesson, we will try to learn about what constitutes electricity, how does it flow in an electrical circuit or electric circuit, what are the factors that control or regulates the current through an electric circuit, and at the end in this chapter we shall attempt to answer such questions. We shall also discuss the heating effect of electric current and its application. Electric current first. It is the flow of free electrons through a conductor. The device which causes the flow of electrons through a conductor is called a cell. Electrons flow from negative terminal to the positive terminal. Electric current flows from the positive terminal to the negative terminal. This is called conventional current. Conventional means it has been accepted by many of the peoples, in the world. By almost all the people in the world, it has been accepted. A continuous and a closed path of an electric current is called an electrical circuit or simply an electric circuit. Electric current. It is expressed as a rate of flow of charge through a conductor or the quantity of charge flowing through a conductor in a unit time. Then electric current I is equal to charge Q divided by time T. The SI unit of electric charge is coulomb. It is the charge contained in 6.25 into 10 to the power 18 electrons. The SI unit of current is ampere, denoted by symbol A. So 1 ampere is equivalent to 1 coulomb by 1 second, or we can also say it is equal to 1 coulomb per second. So 1 ampere is the current flowing through a conductor if 1 coulomb of charge flow through it in 1 second. This electric current is measured by an ammeter. It is always connected in series. So these are the pictures of ammeter. This is a picture of ammeter and another one is for milliammeter. Now here in this ammeter you will see two terminals to be connected here with the red one and the black one. Red one is this one and black one is this one. This red one is meant for connecting the positive terminal and this negative terminal should be connected at this black electrode or connecting terminal, you can say. And you will see here marked as capital A. So this means for ammeter, and the scale to be measured is in terms of ampere. Here you will see 0, 1, 2, 3, 4, 5 like that. So this ammeter can read up to a maximum value of 5 ampere. Got it? And for that of the milliammeter, here you will see black side, black terminal and the red terminal here. So this black is meant for negative. That means you have to connect this negative terminal of the battery or the circuit here and the positive terminal onto this red color terminal. Now here you will also see the scale here, and it is written as small ma. That means the unit to be measured, the current here is to be measured in terms of milliampere, okay? And you will see here 0, 20, 40 like that, and up to 100 here. So this milliammeter can read up to 100 milliampere. Got it? Yes. Next, let's see about the electric potential. Okay, electric potential and potential difference. Electric current will flow through a conductor only if there is a difference in electric potential between the two ends of the conductor. Whenever these free electrons are present inside the conductor also, the electrons can move about inside the conductor from one point to another point in a very zigzag path like this. But if that source of EMF, like that of a cell, if it is connected, then instead of moving those free electrons in a zigzag path like this, rather they will try to move in a particular direction from one end of the conductor to the another end of the conductor. Why such free electrons move from one end of the conductor to the other end of the conductor when source of EMF like cell is connected to it? Why? Because the source of EMF like that of cell or battery creates potential difference between the two ends of the conductor. Got it? So your cell or battery is one of the source so as to create the potential difference between the two ends of the conductor. Got it? So this difference in electrical potential between the two ends of the conductor is called potential difference. When I say potential, it is nothing but it is the amount of work done per unit charge. Okay, that means in transferring that amount of charge from one end to the other end of the conductor, that much amount for every unit amount of charge, we call it that as potential difference. I'm telling you again, potential difference is nothing but it is the amount of work done in bringing a unit positive charge from one end to the other end. Okay, so your electric potential V is denoted by V. So your V is equal to what? Work done. Okay, work done, let me denote it by W only, or you can write work done like this, divided by the total charge that is brought, okay, or that is sent through the conductor. So if you want to find out work done per unit charge, then this will give you the amount of work done per unit charge. So this amount of work done per unit charge, we call it simply as electric potential. Okay, yes. Let's move on. The potential difference in a circuit is provided by a cell or a battery, as I said. Okay, the chemical reaction in the cell provides a potential difference between the two terminals and set the electrons in motion and produces electric current. Got it? So whenever you hear the word potential, you just remember, okay, work done. Okay, so whenever a point is having a potential, that means that point has the ability to do some work so as to push the free electron present in the conductor. So if there is a potential, at the other end there is a potential, and if they are not same, then what happen? Electric current will surely flow from the higher potential to the lower potential. So you need to find out whose end or whose side is having higher potential. So electric current will flow from higher potential to the lower potential. But mind you, your free electrons inside the conductor will move from the low potential to the high potential. Got it? So the direction of the current will be in the direction opposite to that of the flow of electrons inside the conductor. Clear? Yes. So we call it that direction of current which is taken in the direction of the opposite of the flow of electron. We call that current as conventional current. Clear? Yes. Let's see about the potential difference. So it is nothing but the potential difference between any 2 points. If you take it onto the conductor, okay, the potential difference between that 2 points, say A and B, is the amount of work done to move a unit charge from A to the point B of the conductor. Got it? So in a simple word, in a very short way, you can say potential difference means what? This is the difference of potential, okay, of any 2 points in the conductor. Got it? But if you want to write it mathematically, then you have to write like this. Potential difference is nothing but it is work done divided by charge. Okay, so we simply say this as work done per unit charge. Got it? If you are not able to bring that unit positive charge, if you are bringing this much Q amount of charge, then that much total amount of work done, you need to divide it by that total amount of charge, so that you will get work done per unit charge. For example, if you bought 5 pens, okay, so let's take it that for every pen, one pen costs say rupees, say 20. So if you are going to buy some pens with rupees 200, okay, with rupees 200, then how many pens you can buy? So with this 200, that means you need to divide it by 20, then you will get 10 pens, right? With these rupees 200, you can have or you can buy 10 pens. So what is the cost price per pen? That means rupees 200, okay, divided by number of pen is what? 10, right? So instead of dividing by one pen, we are dividing by the total number of pen. So these rupees 20 by the total number of pen, we call it these as cost price of the pen per pen, or simply you can say cost price per pen. So per pen, when we want to find out that per pen, then, or you can say per unit pen, you can say, then you have to divide it by the total number of pens, right? Likewise, similarly, if you want to find out the work done per unit charge, then you need to divide it by the total number of charge. So when you bring that charge from one point to the another point, say if you are going to bring that Q amount of charge, okay, from one end of the conductor to the other end, that means from one end, say suppose A to B, if you are going to bring this Q amount of charge from this point A to the point B inside the conductor, then you need to find out how much amount of work done is, okay, used or is done by taking this Q amount of charge from this point to this point B. Then that total amount of work done divided by total amount of charge that is brought from A to B, we call it this as nothing but this as the potential. So electric potential, rather, because this is a potential difference, because from one point to the another point, so we may denote it this as electric potential difference AB. That means potential difference in bringing that Q amount of charge from point A to point B, that is denoted by total amount of work done divided by total amount of charge. So this total amount of work done divided by total charge, we simply call it this as work done per unit charge. Clear? So that much amount of work done, okay, in bringing a unit positive charge from one point to the another point inside the conductor, we simply call it that as electric potential. And this electric potential is denoted by what? B. And this B is equal to W by Q. Got it? So this B is equal to W by Q is nothing but this is the electric potential difference. So whenever you hear the word potential or potential difference, just you remember about the work done per unit charge. Okay. Now let's go to the SI unit of potential or potential difference. Okay. The SI unit of electric potential is volt. So its potential difference, okay, difference in potential will be also same as what? Volt. So the SI unit of electric potential difference is volt and it is denoted by V. So how we will define this 1 volt? From this equation, from this equation, V is equal to W by Q. If you want to find out this 1 volt, then if this is going to be 1 volt, then it should be 1 work done. SI unit of work done is joule. SI unit of charge is coulomb. Okay, so we may define 1 volt from these expression. Okay, as what? 1 volt is a potential difference when 1 joule of work is done to move a charge of 1 coulomb from one point to the other point. Got it? So we will define it from these expression. So how we will define it? 1 volt is a potential difference when 1 joule of work is done to move a charge of 1 coulomb from one point to the other point. Got it? So 1 volt is equal to 1 joule by 1 coulomb, or you can say 1 volt is equal to 1 joule per coulomb. Got it? You can write this like this. Whenever you have a calculation, whenever you happens to have that calculation, and if you find this 1 joule per coulomb, then you can replace it that joule per coulomb by volt. Okay? Yes. Now, potential difference is measured by an electrical device known as what? Voltmeter, and it is always connected in parallel across the 2 points between which the potential difference is to be measured. So we usually say that ammeter is connected in series while voltmeter is connected in parallel to the circuit. Why this ammeter and voltmeter are connected in series and in parallel respectively? Because your ammeter is a very low resistance, so insertion or connection of ammeter in the circuit in series will not bring any harm to its previous flow of current or potential difference there. Okay, so what happened? This ammeter is a very low resistance device and it should be connected in series, while your voltmeter is a very high resistance device and it should be always connected in parallel. Got it? Let's see the pictures or image of voltmeter and millivoltmeter. Okay, as we have seen in the case of what ammeter and milliammeter, you will also see like this. Voltmeter, it will be denoted by V and it will be 2 terminals, okay, connecting terminals here. One is red and one is what? Black. So these black mark, you will see a negative sign here, so it should be connected with a negative terminal, and the red, it should be connected with the positive terminal. Okay, so this voltmeter can read up to a maximum value of 5 volt. Okay, and likewise here also you will see as MV, that means millivoltmeter. Okay, and this millivoltmeter will measure in the unit of millivolt. Got it? This is of 100. Okay, the maximum is 100, so at the most this millivoltmeter can measure up to a maximum of 100 millivolt. Got it? Yes. Let's see the diagram how it will have to be connected in the case of ammeter and voltmeter. Now this is a battery. Okay, these battery are connected in parallel. Okay, and what happened? This is a key. Got it? Key, or you can call it as a switch. So from a positive terminal it goes to this key, and then from at one end of the key, from the other end, I mean, it will be connected to a bulb. The other end of the bulb is connected to the positive terminal here like this. Why? Because this is a positive terminal. See, this side is positive coming like this, so it should be connected to the positive terminal. The other coming from a negative terminal, it should be connected to the negative terminal or black terminal of the ammeter. Okay, so that this is how your ammeter is connected in series. So whatever the current that is flowing here, that will be also be flown through that ammeter circuit inside it, and it will come out to the negative terminal like this. But in the case of voltmeter, if voltmeter is going to be connected onto this circuit, now let's we want to find out the potential difference between the 2 terminals of these electric bulb. Then we need to connect it here, the 2 terminals here like this. The positive terminal should be connected from here, and the negative terminal of the voltmeter should be connected here. Got it? Let's see. So this is how that voltmeter is connected. Okay, you will see that voltmeter is connecting the positive terminal from here to here like this, and negative terminal from here to this black side. Okay, so this will give you what the parallel connection. Okay, so your voltmeter is connected in parallel to the circuit. Now let me show you another diagram. This electricity. Okay, this is an electric circuit. Now this is a cell or a battery. If it is a combination of more than one cell, then we call it that as a battery. So what happens, even though you see as a single dry cell, who knows, inside it there may be many cells. Okay, and we may call it as battery, right? So from this battery, the connecting wires, okay, it goes to here like this to a bulb, and the other end of the bulb it will go to this connecting wire and coming to the positive terminal like this. So what happened from the battery, what happened, electrons will be coming out and electrons will be flowing in this direction like this. Okay, you follow the tips of my pointer of this, what, your mouse. Okay, this is the direction of electron. That electron comes out from the negative terminal of the battery and it passes through the bulb, and then it comes to this connecting wire again and goes to the positive terminal. So electron flow is in this direction. Got it? Whereas the conventional current will be flowing in the opposite direction. Why we take it this opposite direction? Because at the time of this development or discovery of this current, electricity, then what happened, at that time there was no knowledge of having this electron. Okay, so they thought that the positive charge is flowing inside this conductor and it creates electric current like that. But after the discovery of electrons and all, the charge that is flowing inside the connecting wires or conductor is none other than electrons. Okay, so but the electron moves in this direction, whereas the current will flow opposite to it. So the direction of the current here in my diagram on the screen will be clockwise. Okay, while the motion of electron will be anti-clockwise like this. Got it? So this is the flow of electron, or rather the direction of electron, while the conventional current will be opposite to it. Got it? Let's see in the schematic diagram of a circuit diagram here. Okay, this is a battery, right? Battery is denoted like this. I will show you after this about the what symbol to be used in an electrical circuit. So this is a battery. Got it? And this is a key. K represents key or switch. Okay, and this zigzag line represents what is known as resistor. Okay, we will learn all about this again. So this is just to show you the direction of flow of electrons and that of the current. Now electron will be starting from a negative terminal of the battery. When the key is put to on, then what happened, then electrons will flow here in this direction, right, from the negative terminal to the positive terminal in the external circuit. Got it? In the external circuit like this, from a negative terminal electrons will emit out and it comes back to the positive terminal of the battery again, whereas the conventional current will be opposite to the motion of electrons. Got it? So this is the direction of the conventional current, whereas this is the direction of your flow of electrons inside the conductor. Got it? So now let's see some symbols of the components to be used in an electrical circuit. Got it? Yes, these are some symbols of the components to be used in an electrical circuit, right? The first one is what? Connecting wires. I will not go through all these descriptions. Okay, this connecting wire is just to connect two or more components. Okay, and this is a what? Conductor, and this conductor which is used to connect one component with the other, we call it simply them as connecting wires. Okay, and it is simply denoted by a line like this. It may be straight or curved, doesn't matter, right? But when I say curve, it's not be curved in a particular fashion like this, zigzag like this. If it is like this zigzag, then it will represent a type of a component known as resistor. Okay, these resistors are made up of alloys. Okay, while considering that metal and alloys, what happen, alloys will have considerably higher resistance than that of conductors. Okay, so when you mix up two or more metals in a definite proportion, then we call it them as what, colloy. The resulting substance we call it as colloy. Okay, alloy like that of nichrome, manganese, constantan, eureka, these are all resistance wire. Okay, so that zigzag line will represent what is known as resistor. Got it? And in these resistors, we may have three types of resistors, depending upon the components I mean. So the first one is a normal resistor like this in a zigzag line. The second one is of a variable one. This one is a fixed resistor, okay, of whose value is fixed. But if it is with an arrow here like this, okay, upward or downward, then we call it this as variable resistor. Variable resistor means of whose value of resistance can be changed. We call it that as variable resistor. Okay, and the third one, which is also rather a variable resistor, and we call it that as rheostat. And that symbol is also similar to like this, but the arrow should be here above. Okay, in this, if it is arrow is upward like this, then it represents what, variable resistors. And if the arrow is above, and if it is going to have the ability to slide over these resistors where another terminal here, then we call it that as rheostat. Okay, we call it that as what, rheostat. R-H-E-O-S-T-A-T, rheostat. Okay, got it? And this is that rheostat. So rheostat will have what, three terminals like this. This will be fixed. At the time of practical classes, what happen, if you are going to happen to connect this rheostat, then one will connect here. Suppose one line, say, coming from a negative side of the battery. If it is connected here like this, then the other end should be left free, this one. Okay, should be left free, and the positive terminal should be connected onto this terminal. Got it? So that what happen, when you slide this arrow above this resistance wire, depending upon how many turns are there in the circuit, your resistance in the circuit can be changed. So we call it this rheostat also as what, one of the type of variable resistor. That means it can change the value of the resistance in the circuit. Another usage of this resistor is what, it can be also used as potential divider. Okay, and that potential divider part I will not tell you here, rather when you come to that higher classes I will tell you again. Okay, so your rheostat can be used in two ways. The first one is what, to change the value of the resistor in the circuit. That means it can be used as a variable resistor. And the second one is what, it can be used as potential divider. Okay, now next is about the cell. Two parallel lines of unequal length represents what, a cell. The longer one will represent the positive terminal, and the shorter one will represent what, negative terminal of the cell. If you happens to have a battery, then the battery will be of this type, a combination. Okay, this plus minus, this longer side is plus, shorter one is negative. So positive, negative, positive, negative. So such combination of more than two cells, we call it as what, battery. Here in this diagram, this is a battery of how many cells? 3 cells. So 1, 2, 3. Got it? Positive, negative, positive, negative, positive, negative. So this battery consists of 2 cells, we may say. Okay, and we left it to this one symbols. So this symbol is for none other than your fuse. An electric fuse will represent by this circuit, by this symbol. Okay, it is just like the shape of S. Got it? It is just like the shape of S, like this, with these 2 terminals here like this. Okay, in this way. So this will represent what is known as switch, and this will represent the plug keys. Okay, this will represent the plug key like this. Let me see, let me zoom in, okay, just to make you see clearly. So a plug key will be represented like this. It is just like a semicircular arc like that. Okay, semicircular arc, okay, with the two terminals like this, without having any dot in between the arcs, okay, the circular part. Then this represents open circuit. That means the current is not flowing from this side of the terminal to the other side. Okay, this is just like your off in the switch. Okay, current is off, or you can say current is open, you can say. Okay, in the closed circuit, what happened, a dot will be there in between these two curved semicircular parts. Okay, then what happened, this dot represents what, closed key. That means your plug key is plugged and it has been connected, and so the current can flow from one side of the key or a plug key to the other side. Got it? This is what about your symbols. And let's see some more symbols also. The next one is your electric bulb. Okay, let's see. Now in an electric bulb there is a curve like this. Okay, this curve, okay, line with two straight lines, horizontal lines, this will represent what is known as an electric bulb. Okay, this will represent the filament of the bulb. Okay, and these are the two terminals. In some book also you may find the bulb, the symbol of a bulb, just like the diagram of or a figure of a bulb like this also. That will also do. Okay, like this, two terminals like this. So this will also represent a bulb. Got it? And if you don't want such type of that large drawing and all, you can simply represent by the above one that is given here. Okay, the first one, I mean, that will represent what is known as what, bulb. Now next is what, connecting wires. Okay, connected together. If the two wires, okay, one horizontal and the vertical, if they are connected here, then it should have one dots there like this in between this line, connecting line, and this connecting line. They are connected at this junction, right? So there should be one dot like this. Okay, one line. That means this is a connecting wire, this is also another connecting wire. So if they are connected or if they are joined, then there should be a dot mark here like this. Got it? Yes. And in the case of that of wires which are not connected, even though by simply drawing the two lines, okay, one above the another, it doesn't mean that they are connected. Okay, they may not be connected also when we look to that circuit. So in order to represent such type of circuit which are not connected to each other, then that two connecting wires, one vertical and another horizontal connecting wire, if they are not connected to each other, then a curved line where there is having that intersection, okay, that represents what is known as what, wire not connected. Okay, see, in this it will be curved like this, right? So this curved line represents what, in between these two vertical and horizontal line, this represents what is known as two wires not connected. Okay, a voltmeter, we have already seen this one. A voltmeter will represent by such a symbol in a circle. Okay, in a circle with a B mark there. Okay, simply like this also it will represent voltmeter and ammeter. So it should have two terminals, one positive and one negative here. So this represents what, that should be connected with the positive terminal of the circuit or a current, and this will be the negative terminal. Okay, so your ammeter and voltmeter are having positive and negative terminals. Okay, and instead of drawing like this the symbolic representation for voltmeter and ammeter, there may be also another way. You just represents by a circle like this with the two terminals. Okay, mark it positive and negative, and if it is drawn with an arrow on it and mark near to it as A like this, then this will represent what is known as what, ammeter. Got it? Got it? And if you happens to wants to draw what is known as voltmeter, then instead of this you simply what write the letter V there, okay, just near to it. V, positive terminal, negative terminal, like this. Then if you write it V, then this will represent what is known as what, voltmeter, not ammeter this time now. Okay, so it will represent what, voltmeter. Why? Because we have already written there near that arrow, we represent it by what, V. So this will represent what is known as voltmeter. Clear? Yes. Let's further go to the next symbols. Now in the case of alternating current means the current of whose magnitude changes continuously and it changes its sign periodically. We call it that as alternating current. Whatever we are having from the line, okay, community line to our home, we call it up to onto our house, we call it that as what, alternating current, AC current we simply call it. So that alternating current will represent by a symbol that is just like S, okay, shape here. So we call it this symbol as what, AC current. Clear? Yes. Let's see for the next one. This is very important for your class 10. This is known as Ohm's law. What is this Ohm's law generally? Ohm's law is nothing but this is a relation, okay, relation between what and what, potential difference and the current flowing through the conductor, right? What does it state? Ohm's law states that at a particular temperature, okay, or rather if temperature is kept constant, then it states that the current flowing through a conductor, okay, inside the conductor is directly proportional to the potential difference between each end. That means between the two ends of the conductor, okay. Or you can write the statement as it is also given here. That means what, I is directly proportional to V. Or you can also write I means current, okay, V means potential difference. Or you can also say V is directly proportional to I. Got it? So whenever there is a difference in potential, then current will flow surely from higher potential to lower potential. We also know that from the higher level to the lower level, water flows. Okay, so water current flows. When I say current means nothing but it is a motion. In our case of electricity, current means what? Motion of what? Free electrons. When we say water current, it is nothing but the motion of water molecules. Got it? Just like that. So what happened? Your I is directly proportional to V. That means current flowing through the conductor is directly proportional to the potential difference, or you can also write potential difference is directly proportional to current. Got it? Or V by I is equal to constant. When we say like this, okay, we need to see it with what changes the current changes, okay, with what changes the other variable changes. With the difference in potential, current changes. If the difference in potential is more and more, then what happened? The current will be also more and more, right? If the difference in level of the water is more and more, then the water current is also more, like that. So with the difference in potential, current depends on that difference of potential. Got it? So V by I, if you try to write it that disproportionality into equality, then we will require a constant, right? V is directly proportional to I, right? So if you want to change this proportionality symbol into equality, then we will write V is equal to what? IR, like this. So this R is nothing but this is a constant of proportionality. The constant that we use in changing from proportionality symbol to equality symbol, we call it that constant as constant of proportionality. And this constant of proportionality in the case of electricity, we call it this as what? Resistance of that conductor. Got it? And it depends upon the length, the cross-sectional area, the temperature, and also the material of that conductor. Okay, we will discuss this part in the latter part of today's topic, but first let's try to prove this Ohm's law first, okay, before proving that. Or we can do like this: instead of this constant we may replace it by R. So we will write it that potential difference is equal to the product of the current and the resistance. Got it? That proportionality constant resistance. We will also try to define this resistance, okay, later on. Now let's try to verify it, okay, this Ohm's law. How to verify it, this Ohm's law? Now, as you might have learned in your mathematics also, if that while drawing graph, if that graph comes out to be a straight line, then what happen? The variable x and y are directly proportional, okay. So if we are going to draw what potential difference versus current graph, then in that graph, if it is coming out to be a straight line, then that verifies your Ohm's law. That means your potential is directly proportional to the current. That means if we are going to draw this potential difference versus current graph, and if it happens out to be graph to be a straight line passing through this origin, current like this, V like this, potential difference, current drawn along x-axis, y drawn along y-axis, and if that graph comes out to be a straight line passing through this origin, then what happened? We may say that your V is directly proportional to I. If that V is directly proportional to I, that means what? That is nothing but your Ohm's law. Got it? So let's try to verify this by having an activity, okay. By having an activity means the data that had been done by doing that activity, okay. Verification of Ohm's law. So to do that, let's take it a circuit diagram like this. This is, let me zoom in, okay, just to make you see clearly. This is circuit diagram, okay. This R is a resistor between the two terminals A and B, okay. These are the connecting wires, got it. And this is a battery, and we make it in such an arrangement that the terminal of this key, it can be changed here at this by using one cell, two cells. If I remove this terminal, and if I connect it here, then in the circuit there will be two cells. So a battery of two cells will be included in the circuit. If I remove it here and if I connect it here, then three cells will be included in the circuit. Likewise, you can change the number of cells included in the circuit. Got it? With this change in the number of cells, you may also have the difference in potential. More and more number of cells means what? More potential difference will be developed across these two ends of these resistors A and B. Got it? So ammeter is connected in series like this. So see, this is a positive terminal and it should connect to the positive terminal of the voltmeter, right? And what happened? While going to that negative terminal, again this side is coming from the positive terminal, and you need to connect it for the positive terminal of the ammeter also. Got it? Here. And then through this negative terminal it goes to the key, plug key, and from this one end of the key it will go to the this changing terminal of this battery. Okay, now let's see. Now in my experiment or activity here, we are going to change the potential difference by changing what? By changing the source of EMF. EMF means electromotive force. This electron is made to move by means of this source. So we call it this as what? Electromotive force. This is a pseudonym, okay. By the chemical reaction, electron will try to push out from that negative terminal of the cell, okay. Now with this, we will try to go to that description part like this. Let's see. Set up in the circuit diagram as shown in the diagram here. First use one cell and not the current, okay, that is flowing here in the ammeter, and the potential difference across these two ends by the voltmeter. So you keep on noting down these two pairs, one for the potential difference across this end and the other is the ammeter, that means the current read by this ammeter. So you will have what? The other pair of V and I. So for the first one you note it down as V, and for this emitter you note down as what, I1. For what? When you use only one single cell in the circuit like this, okay, in this. Got it? And then next you try to make this as an order pair. We need to plot it later on, okay. Then in the next case you try to include two cells in the circuit, so that what happened, the connection will be here only. Got it? In this. Clear? Then at this time what happened, let's see the potential difference, okay. The potential difference be denoted by what, V2 and I2, and let's make it this as the second order pair. So when this what, battery is here connected, that means two cells are connected, then what happened, the voltmeter, the potential difference read by this voltmeter is denoted by V2, and the current that is read by this ammeter, let's denote it by I2 for the second one. Similarly, if you keep on changing this to the third one, the fourth one, you will have the such order pairs, okay. And if you plot it, then you need to see what is the nature of that graph, okay. That graph will be surely a straight line passing through the origin, okay. That graph is drawn here, okay. Let me not show you that one because this graph is little bit different. So let me draw you the graph with my hand, okay. So while drawing your graph, let's be taken this as x-axis and this as y-axis like this. So what to be drawn on x-axis and what to be drawn on y-axis, that should be very much what, understood first, okay. Whatever that is independent, that to be drawn along what, x-axis, and that depends on some another variable or factors, you need to draw along what, y-axis. So in my case your potential difference V should be drawn along what, x-axis. So let me denote it by PD, okay, and it will be in terms of V like this. And your current I should be drawn along what, y-axis, and that graph will be surely passing through the origin, and it will be a straight line, okay. While I'm drawing, as I'm drawing with my mouse, I cannot draw it in a very fine straight line, but it will be a straight line like this. It will be a fine line, okay, not like this with a blunt or a broad what line, but it will be a fine line like this, okay. It will be a straight line passing through the origin, okay. Your V along x-axis and your current along y-axis. Got it? But in some cases, by using instead of these variable cells, if you happens to use rheostat, and if current is match change, and depending upon that, if you try to measure the potential difference, then the graph will be same like this, similar like this, but the axis, okay, along which what is drawn, that will be different. In my case, I drew it that potential difference along x-axis, but in such case your graph will be drawn in this way. Your current will be drawn along x-axis and potential will be drawn along y-axis. In that graph also you will get it, the graph, a straight line passing through origin. This shows that what, your potential difference is directly proportional to current, which verifies your Ohm's law. Got it?